Hi, this is the video for checking your answers on the Hooke's Law simulation worksheet. So before you watch this, make sure you finish the worksheet by yourself until the end of the worksheet, which is page 5. Without further ado, let's get started. So first of all, you have to go to the simulation, which is here. And yeah, here's a tab that we're going in. And then you have to select the movable line, which is useful for you for maybe measuring later on, and also set the damping to be maximum, and also take out the ruler as well. Damping means friction. That means when you try to weigh, it will take like shortest time for it to be stable, or if you set it as the default, it will be keep bouncing. So that is a difference. The other way you can do it is click the red button. So that would be an immediate stop. But I feel like using damping would be more like natural, as if you're doing the real experiment. Anyway, so the first thing that we have to do is to change the spring constant to smallest first, because this is the first thing that I want you to do. And since you have done it already, so I'm going to speed up a bit. What we have to do is to measure the original length. So original length is really up to you how you would like to measure, but the most important thing is you have to be very consistent. So for me, I will choose really literally the starting point here to start measuring with the ruler, and then I will be measuring the very end, very tip of the spring. And so here I would say the reading should be 48. So I'll take the initial or original length to be 48 cm. So I don't have to type unit because cm is already put down here. And then we will start with the mass, which is 100 first. Okay. And so now I think it's now okay. And then I will be looking at here. I think this one should be, well, to be honest, I think it's 80.5. But I will take the closest interval, so that would be 80. Okay, so I will do 180. And in fact, I would say I am going to, because we are going to do 7 different set of data, so I'll do 50, 150, and then 200, 250, 300. Oh wait, yeah, because this is the range that we can do, right? So I think we have to add one more. You may argue we can start with mass 0 and getting the total length to be same as original length 48, but that wouldn't be a very meaningful data. So I guess I would just add one more here, so 275, and that will make us 7 different set of data. The reason why we need 7 sets is we can then get a better accuracy when we try to find out the trend, which is the line of best fit on the graph eventually. Okay, so for now, let's go and check out other data. So the 50 gram, that one would be 64. Okay. And then 150 would be 97. 200. Okay, here you find there's an issue because, well, obviously the ruler isn't long enough. So one way of doing it is you could use these to help. Okay, so this is the starting. And then, oh wow, you can't even move the ruler down. Okay, never mind. I think we will do a slightly more complicated way. Okay, so we remember we actually start from here. This is 100, and then we will go up to here, and this is actually 23. 23, that's right. But then we actually start from 10, so it's actually 113 instead. Okay, so that's something, yeah, it happens, but then maybe it may not happen in reality because this is a simulation. But I guess you are still smart enough to get rid of the problem, right, by using different approaches. Okay, now let's go to 250. Okay, then I guess we have to do this again, and then we have to start the ruler here, and then I believe this is 39, so 129, because again I start with 10 cm. 275. Okay, we'll do again here. I'll say this is closer to 48, so 138, and then lastly 300. Okay, hopefully, luckily we still see the spring. Okay, so it will still work. Oh wait, I can't lower that, but then never mind, I can still read it. I think it's 56. Yeah, so 146 in this case. And one thing you may want to check now is to quickly see if your data would be kind of fitting with the theory, because according to Hooke's law, then we should know that whenever you add something, then of course the total length will be longer because the extension will also be longer. And since here we add 50 each time, then supposedly the extension increase would also be the same. So here we see is plus 16, here is plus 17, I guess. Okay, here is plus 16 also, here is plus 16 also, which is pretty good. Here is plus 9, yeah, but then the thing is because here to here is only 25 grams, so that's why it still kind of makes sense. And here is plus 8, yeah, I think, yeah, this is pretty good. Yeah, so I think the results should be pretty nice on the graph later on. Alright, so now we'll repeat the same procedures for the largest spring constant. So here we have to select this, and I think we'll do the same thing, so then it is more like comparable. And so for the independent variable, we'll be following the same choice. And then I believe the original length should be the same, but then I'll still measure it again. Wait, actually I think it's 49. Yeah, maybe the thickness kind of affected. Maybe it was meant to be 48. I mean 49, and earlier I thought it's 48. Never mind, I'll just stick with what I observe. So the first data is actually 50, so let's start with 50. And so here I actually really need, wow, it's really hard to see. Okay, that's fine, I'll take it as here. So as long as we are consistent, then it should be alright. So here is 53. Okay, and 100 gram. Will be 57. 150 gram. Going to be 61. I think you can see the trend is always plus 4 here, but then even though you know that's going to be trend, you should still perform the experiment. It's 65, yeah, which is perfect. 250 gram. 69. plus 4, yeah, that's what you get. $75, and then that's not going to be a big change, so 71 I will call, and then lastly 300. Um, 73. Oops. Alright, let me show you how we can do it on Excel, or just an additional information. So you can copy all these total length from the thin one and the thick string of its total length to Excel. So this is what I did. And then, because I know the original length is 48 for the thin one, so all this I'll do equal this minus 48. Okay, and then copy, drag, paste. Okay, that will be done. For a thick one, the original length was 49 according to our observation. So for all this length, I'll minus 49. Okay, and this will be the extension that we have. So I'm going to copy back to here, and then copy this to here. Yeah, which is going to be the same. Just to give better formatting, I'll do this. Okay. And of course, you can do it manually. The reason why I like to do it with Excel is since we have inputted digitally, then yeah, why not? And also that will reduce your careless mistake also. Anyway, so we will move on to plot a graph of extension for both string, extension against tension. Alright, so now we are moving on to the graph, and I've got the x and y axis already, and because that would take some time for me to do it on computer. For you, if you're doing it on a piece of paper, it should be very easy just to use a ruler and draw it. And usually one key idea that you should have is you should try to use as much space provided as possible, because when you try to make a graph, that will make your precision better. Imagine if you try to make a graph that is this tiny, then those data point is pointless, right? It's not meaningful, because that is not going to be very accurate. With the many grids that you have, then the data point that you plot is going to be more accurate. And so before we get to the point, we should label the axis first. So usually we'll have extension, which is the dependent variable to be the y-axis. So that's why this is the graph that I asked you to make. So extension, and then the unit is going to be cm. That's totally fine if you don't have to change it to meter, as long as later on you understand the meaning and the unit of the slope. Here will be the force, which is going to be the tension, and then it's in the unit of Newton. The next thing that we'll do is usually the hardest part people find, which is defining the range of your x and y axis. And I said it's difficult because people may usually choose a range that is too wide, and eventually the data point that you cover is probably only within a small region, and that means it is not a good choice. So the way that you should do it is by looking at the range of the data that you should have. So for tension, it's going from, for both, it's going to start from 0.5, so maybe 0 to 3. And so here, what we have to do is we write 0 here, and think about at the very end here, around here, this should be nearly 3 at least. So for now, if you need to divide the grid equally, then one thing that you probably would need to do really is to count how many grids are there. But other than counting, what you could also do smartly is to use a ruler and measure how long the space will be given, and then you can then roughly see how much space you need for each interval. So here, because I'm doing it on the screen, I can actually make it smaller because my ruler is not long enough. So here I've got about the whole x-axis about 15 cm for me. Okay, it will be different for you, but for me it's about 15 cm. So if that's the case, since I have to divide to up to 3.0, so that means for each of these 0.5, probably I can do if 15 is 3.0, then 0.5 is going to be divided by 6. So 15 divided by 6, it's going to be 2 point something, yeah? 2.5. So maybe around at 2.5 on my screen, which is about here, I think. Yeah, about here. Then that should be 0.5, which is 1, 2, 3, 4, 5, 6. Yeah, that actually looks pretty nice to me. And then I can continue with this interval. This is not easy, again, this is not easy. And so once you decided it, then you stick with this. 6th grade, 1, 2, 3, 4, 5, 6. Okay, here. 1.0. 3, 3, okay. And make sure you do it regularly. 3, 3. Okay, 2.0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And then you may say, hey, what about the rest then? A tiny bit is fine. The rationale or the criteria is you have to use at least half of the graph paper. So this tiny bit is fine as long as you exceed half of it. I would say not really half. That would be a really low expectation. I think you should aim at about 80% of the graph paper. Okay, so now let's try to do the same thing for y-axis and give it a suitable scale. And so now what I can do is I can zoom out. Again, if you can use a long ruler, that wouldn't be a problem for you. For me, I would like to adjust so that now it is again 15 cm in this ratio. And for one for 1 cm, it's going to be 3 small grid. And so that means there will be a total of 45 grids. So I don't have to count, I can do this calculation, fine. There will be 45 grids in total. And if I look at the y-axis value, I have to entertain up to 24 and 98. So actually we only take up to 98. Right? 24 is smaller, so ignore it. 98 is the largest data that we have to plot. And let's take it as 100. How about that? And 45 grid to entertain 100 here. How about we just take 4 grid for 10 cm? Okay, and I think that should work. And we'll be pretty much using all of them. So here we have 1, 2, 3, 4. Okay, zoom in a bit more. 4 grid to be 10. 4 grid to be 10. And you want to choose something that is sensible as well, because otherwise it will be hard for you to plot and find the data later on.
60, 70, 80, 90,
100, and that's actually enough. Yeah, and yeah, we are actually very good. Nice. Okay, so we have done the hardest part already, and we just have to now plot those data on the graph. And so the first data is going to be 0.5 and 16. I probably will change another color. Okay, so 0.5 and 16, so that should be roughly between half and slightly higher. Okay, and you should use a cross to plot it. And then the next one is going to be 1.0 and 32. Okay, 32. This is 35, so yeah, 32 should be around in the middle. And so that should be all for the rest of the data, so I'll skip that part. Okay, so here are the data point, and now we have to add the line of best fit. And so for the thinner one, ideally you should go through the origin. Okay, let me make it thicker to show like more easily. And then I do think, however, even I mean, in theory, you should pass through the center. But then when we try to look at the data, you can see here, here, and here, there are like 3 data points that is more like below the line. So I think we really have to follow what data told us and adjust accordingly. So Yeah, I believe these will probably be the line that I'll draw, which I would not be able to draw through the center, but that's okay. That happened in experiment. Well, not really. It's very close to center, but not really passing through it. For the other spring, okay, we can make a rough one, and then I'll change it to green, make it thicker, and again, it's way easier if you do it on a piece of paper. And I think this one is all right. Yeah. And then when you try to draw a line, you don't have to stop at the last data point. You can always extend it further. Okay, like this. Okay, so this will be the line of best fit for the two spring. Now we'll be moving on to further questions. So question 1, state and explain the physical meaning of the slope. And without recalling, what you should do instead is by deriving. So when you look at the graph, then you should be able to say the slope will be rise over run, and that should physically mean extension over the tangent. And by recalling the Hooke's law itself, which is F equal to Kx, then what we will get is we can get extension, which is x divide f, okay, and in this case then we'll have 1 over k on the other side. So that means the slope will actually means 1 over k, which is 1 over spring constant, or spring constant inverse, if you like to write this way. Question number 2, did the spring reach limits of proportionality? How do you know? If you recall what you learned about Hooke's law, then you should know that when the spring is reaching limit of proportionality, then this graph will start to curve and bend. It will no longer be a linear straight line. And so in this case, we haven't seen it yet. From the data, it's very clear that it's still maintaining a straight line. And that also because the simulation did not consider the limit of proportionality. So that's why it will keep be, really like a constant. In reality, if you keep adding and adding more, then definitely sooner or later you will hit that point of limit of proportionality. So in this case, I would say no. All right. The reason is, according to the graph, the line of best fit is always straight. Okay, don't say linear, because linear is like a more complicated idea, and it's a word that you can't expect an ordinary person can understand. So you should use the word straight line. It's always straight within the data range. So we can't say about the future, like when it is over 3 Newton, but at least within our data, it is a straight line. Number 3, using the graph, find the spring constant of both springs. So referring to question 1, because we know the slope is 1 over k, that means as long as we find the slope and inverse it, then we can find the spring constant. So in this case, then we can find the slope for the thin one, and then separately we can do the slope for the thicker one. Alright, and to find the slope, it's just mathematics where you find delta y over delta x, or you may also write y1 minus y2, x1 minus x2. So let's get back to the graph and look at the line of best fit. One usual mistake that people would make is they look at the data point. So instead of using the line of best fit that you did, you go back to just use those raw data or process data on the data table and find out the slope. And that is not really good, because if this is what you can do, why do you bother to draw a graph then, right? There's no point. So whenever you try to take the slope, you want to calculate the slope, you want to take the data point, or a point simply, on the line instead of the original data point. So ignore all the data point that you draw. Those are not really the most important now, look at the line of best fit. So for me, one other thing that you should do is you should take as long distance as possible of the line. More portion, the better, because that will reduce the percentage error. If think about this, if you take a tiny triangle like this, right, you may say, oh, mathematically these slope should be the same as the whole thing. But the thing is, when you try to read off these data and this data, they may have uncertainty also. They may have absolute error also. So it's always safer and reducing the percentage error when you have a longer portion. So what I'll do is I'll usually go for the two extreme. I would say the first data point is not really 0, 0. I would say it is, this is 0.5 divided by 6. Wow, that's actually divide by 6 and then divide by 2 again. So this is like 0.04 and 0. So this is the first data point. And then I think I would take this one, which is 100, and then the x value is going to be something like, it's really hard for me to see this big screen, but then this one should be, I think, a bit more than half. So it's, I think it's, we can say it's about 3.05. okay, and so yeah, I think that's the data point I'm going to take. Is it fair? Yeah, I think it's pretty fair. So we have, for the thin line, the y is going to be 100 minus 0, and for the x, what was it again? 3.05 minus 0.04, I think. Yeah, and that should give, using the calculator, 100 divide 3.01 actually. So about 33.2, and 3 sig fig, yeah, I think 3 sig fig would be good. So 33.2. And the most important thing also here is the unit, right? Don't miss it out. And you just have to refer back to what we did. So it was cm against Newton, so cm per Newton in this case. Okay, and since we want to find actually the spring constant, so K spring constant is going to be 1 over the slope, and so that is simply, you can use, oh, actually I should take the whole number then. Yeah, it's going to be 0.0301. Actually, like, that will be so easier, so much easier. Newton per cm. Okay, that's the thin one. For the thicker one, okay, that's the same thing. And I should take data point, which is, of course, I will take origin, so 0, 0. And then the other point that I think this point is legit, right? So these should be what? These should be 27.5, and then these should be 1, 2, 3, 4, 5, 6. So that should be 3.5. Okay, 3.5, 27.5. Okay, minus 0, 0 for the origin. So then mathematically it is 7.857 something, and then you can once again write 3 sig fig, so 7.86 cm per Newton. But in fact, the most important thing is for the K, which is the spring constant, for the thicker spring, it's going to be 1 over slope again, so it's just 1 divide this. So I think you all should understand for now. So what I got is 0.1272727. So 1.2727. So 0.127 then. Okay, Newton per cm. So that is going to be the spring constant for the thickest one. And that also makes sense because for the thicker one, you need to have a greater force compared to the thinner one. Thinner one is so easy to stretch, right? So easy to pull. And so the number here is less because you require less force for the same cm. For 1 cm, here will require more force for 1 cm. Question 4 is very interesting because it wants you to find the unknown, right? These mass in red color. So going back to the simulation, this is the mass we want to find, and then so you have to think about how we can find the mass. One easy way to do is you can use what we have learned about the spring constant, and then in that case we can simply find out by looking at its extension and the corresponding force and then calculate the mass. And so here we can either use the one with the greatest spring constant or the smallest one. But the thing is, with the smallest one, you really literally cannot see the block. So sorry, I think the only way you can do is go for the large one. Okay, and then you can measure its total length. Okay, and that is going to be how much? I think 79. Yeah, 79. Okay, so we have to describe, right? So describe. So what we say is using the thick spring with red block or the red mass hanging on it, the total length that we measure is or equal how much again? 79 cm. So extension by subtracting it, so 79 minus 49, I think. Let's double check again. I think it was 49 earlier. Yeah, 49. And so the extension is going to be simply 30 cm. Okay, so by F equals to Kx, we also get to have mg equal to Kx, because force is the weight. I mean, force is the tension, and tension is the weight in terms of magnitude in this case. So m equals to K, which is the one that we found, 0.127 times 30 divide G, which is we use 10, so let's just use 10 here. So eventually just times 3 actually. So 0.381 kg, because I think earlier we used kg also. So yeah, that should be the mass that we should have. Alright, lastly, if you know how to do question 4, then you should know how to do question 5 because it's very similar. So once again, we could change the gravity to planet X, and that is an unknown. But then we can stick with a known mass, or actually the red one is already known as well. But yeah, I think in case that one is wrong, so I'll stick with this one. So here we've got the spring. I'll still use the largest because the smallest one, yeah, once again, it's not really good. So I guess this one, because earlier we can measure it when we are on Earth, 9.8. So I think this one is even lower, so it should be a greater gravitational field strength than the Earth. Anyway, I will stick with the large spring constant, and then here the total length is going to be 84. Okay, so same idea you can say about again using thick spring and 300 gram, the total length, of course we have already changed to planet X, total length would now be 84 cm, and so the extension is going to be 84 minus 49, and calculating that, it's going to be 35 cm, and then by Hooke's law again, F equal to kx, and again changing the force to the weight, and this time we know the mass, which is 300 grams, which is 0.3 kg, but we don't know the g. For k is the one that we got earlier, which is 0.127, so that's why there's a purpose that we did the experiment earlier. And x here is 35. We don't have to change it to meter because 0.127 is already in Newton per cm already. So these two per cm and cm will cancel out. So you don't have to change them to meter. It's going to be the same. So eventually G 0.127 times 35 divide 0.3 is going to be 14.816666. Okay, so roughly I'll take 2 sig figs, so 15 Newton per kg, or you can use the symbol unit as acceleration, gravitational acceleration, meter per second square. They are both the same. So this is the G for planet X. That's all for the walkthrough. So I hope in this video you don't just learn about Hooke's law, but also the idea of how to plot a graph in physics, how to make use of the graph, and how to interpret the graph also. I hope you enjoy learning physics with me. If you do so, please hit the like button now and subscribe to my channel. I'll see you again in the next video. Bye.